All right, let's talk about something kind of wild. Every single time you send an email, stream a show, or just load a website, there's this invisible war going on. It's a nonstop battle to keep your information from getting totally scrambled. So today, we're going to meet the unsung heroes of that fight, the unseen guardians of the internet.
I mean, have you ever really thought about it? The internet is a fundamentally chaotic place. So what is it, exactly, that stops your carefully written email from showing up as just a bunch of random nonsense? Well, the answer is this incredible set of rules and protocols working tirelessly behind the curtain. So we're going to follow this data on its rescue mission, and we've broken it down into 5 stages. We'll start with the dangers it faces, then meet the lookouts who spot trouble, the medics who can fix things right away, and even the command center that calls in reinforcements. And then at the end, we'll get the full mission debrief.
Okay, first things first, let's set the scene. Imagine your data is chopped up into these tiny little pieces called packets. Now, each one of those packets has to travel across this huge, noisy, unpredictable network. It's a really dangerous trip and, stuff can go wrong. This is the core problem of data corruption.
So meet our hero, a simple little piece of data, just a string of ones and zeros. It starts its journey totally perfect, exactly the way you sent it, 7 digits, all correct.
But then, disaster. Some random bit of electrical interference, a noisy line, whatever, and just one of those digits gets flipped. A 1 becomes a 0. Now that might not seem like a big deal, but that single tiny error can make the entire message completely useless. This is the enemy. So, how in the world do we even know that happened? Well, that brings us to our first line of defense, error detection. You can think of these protocols as the lookouts, right? They're the ones up in the crow's nest constantly scanning. Their only job is to scream, "Hey, something's wrong," when they spot trouble. And our simplest lookout is the parity bit. It's this super clever, almost ridiculously simple trick. You just tack on 1 extra bit to your data, and you do it in a way that makes the total number of ones either even or odd. So, if the receiver gets it and the count is wrong, bingo, you know there's an error. Now the trade-off is it's incredibly fast and simple, but it can really only spot a single mistake. But what if you're up against a tougher enemy, like a whole burst of errors all at once? For that, we need a much more powerful detective. And that's where the cyclic redundancy check, or CRC, comes in. This one is way more sophisticated, and it's incredibly good at spotting when multiple bits in a row have been corrupted, something that simple parity bit would just completely miss. The magic of CRC is that it basically turns your data into a unique math problem. The sender runs this special calculation on the data and sticks the answer, the remainder, onto the end of the packet. Then, the receiver gets the packet and runs the exact same calculation. If the remainder comes out to 0, it's perfect. We're good to go. If it's anything else, alarm bells start ringing.
Okay, so spotting an error is one thing, but what about actually fixing it? For that, you need a specialist. This is where our field medic comes in. This is the one who can perform repairs right there, on the spot, without having to call all the way back to base for a fresh copy. And our star medic here is called the Hamming code. This thing is just brilliant. It goes one step beyond just detecting an error. It can actually find a single-bit error and fix it instantly. It's like having a self-repairing system built right into the data itself.
So how does it do that? Well, the secret is in the really clever placement of some extra check bits. It's kind of like a game of 20 questions. Each of these special check bits covers a unique group of the real data bits. By looking at which of the check bits come back wrong, the receiver can actually triangulate the exact position of the one faulty bit and then just flip it back. It is an unbelievably clever way to not just see a problem, but to pinpoint it and solve it.
But what happens when the damage is just too much? What if there are multiple errors, or an entire packet just vanishes into thin air? Well, that's when our field medic is overwhelmed. It's time to escalate. It's time to call the command center.
And this command center is known as ARQ, which stands for Automatic Repeat Request. Its strategy is really simple, but it is incredibly effective. If you get a packet and it's broken, don't even try to fix it. Just ask the sender to send it again. This is the ultimate safety net. It makes sure a perfect copy gets through no matter what. So how does this work in practice? It's all about this constant feedback loop, this conversation. The sender shoots over a packet, the receiver checks it, maybe using that CRC we talked about. If everything looks good, it sends back a little thumbs up message called an acknowledgment, or ACK. If the packet is bad, the receiver can just say nothing. And that silence is a signal to the sender that it needs to try again.
Now, this command center isn't a one-trick pony. It actually has a few different plays in its playbook, depending on the situation. Let's look at the three big ones: stop and wait, go back in, and selective repeat. Stop and wait is the most basic. It sends one single packet and then literally stops and waits for that ARQ to come back before it even thinks about sending the next one. Super simple, but man, it can be painfully slow. Go back in is a bit smarter. It sends a whole pipeline of packets. But if, say, packet number 3 gets corrupted, it has to go back and resend not just packet 3, but everything that came after it too. Better, but still pretty wasteful.
And that brings us to the most advanced strategy, selective repeat. This is the smartest of the bunch. If packet 3 is bad, it just requests a do-over for that one specific packet. The receiver then cleverly holds on to all the other good packets and just slots the brand new correct packet 3 right into its proper place when it arrives. Now here's the catch. It's by far the most efficient, but it's also the most complex. It takes more memory and more brain power on the receiver's end.
Okay, mission debrief time. Let's pull this all together. We've met our whole team of Guardians now, and each one has a totally critical role to play in protecting our data on that crazy journey across the internet. So here's the whole lineup. You've got your lookouts, Parity Bit and CRC, whose only job is detection. Then you've got your field medic, the Hamming code, who can handle on-the-spot correction for those smaller injuries. And finally, you have the command center, ARQ, which takes care of full-blown error recovery by just calling for a new copy.
And here is the most important part of this whole thing. None of these Guardians work alone. They operate in layers. A system might use CRC to detect an error, realize it's way too big for a Hamming code to fix, and then that triggers an ARQ request to get a new packet. It's this layered defense system that makes our digital world so unbelievably resilient and reliable.
So, next time your email just shows up perfectly, take a second to appreciate this invisible army that's working for you. Now that you've met the team, the simple lookout, the clever medic, and the master strategist at the command center, which one do you think is the real unsung hero that's keeping our digital world from collapsing into total chaos?